Imagine asking an AI, find a table for six tonight at 7:30 near Indiranagar. Keep the estimated bill below 4,000 rupees. One guest has a peanut allergy, and ask me before booking. A chatbot might list restaurants. An agent can search live options, reject those that fail, adapt when tables vanish, and pause before booking. All names, prices, and availability here are fictional. What makes this behavior possible is not magic. It is a loop. An AI agent is not a digital person. It is a software system built around a language model. The model helps choose what should happen next. Instructions define the task, constraints, and boundaries. Tools provide specific abilities, such as searching a database, reading a menu, using a calculator, or creating a reservation. Ordinary software around the model stores the current state, executes approved tool requests, checks permissions, records what happened, and decides when the run must stop. The model is an important decision-making component, but it is not the whole agent. The request contains smaller goals. Find nearby restaurants. Check a table for six. Estimate the price. Look for reliable allergy information. Present acceptable choices. Get approval, then reserve. That plan is provisional. If the first restaurant is full, the route changes. If every suitable option exceeds the budget, the agent may need to ask which constraint can move. Some agents create an explicit task list. Others choose only the next action at each step. So planning does not require a mysterious separate brain. For our animation, we show a concise plan and its updates, not private hidden reasoning. Tools connect the model to outside information and actions. In a common function calling setup, the application first tells the model which tools exist and what arguments each one accepts. The model may return a structured request, such as search tables for six near Indiranagar at 7:30. Application code or a managed tool runtime performs that request. The result returns no tables, three candidates, or an error. The model uses it to answer or request another tool. It does not gain unrestricted control of the restaurant system. It can access only the capabilities developers expose. Read tools gather information. Write tools change the world. A search is a read. Creating a reservation is a consequential write, so we place it behind approval. A multi-step system must carry information forward. Current state includes the user's goal, constraints, tool results, completed steps, and unresolved questions. It may sit in the model's current context. Longer-term memory is usually external, a database, file, summary, or retrieval system that brings selected information back into context later. That is not human-like remembering, and the model's underlying weights normally do not change during this dinner task. A saved preference, such as vegetarian food, may be useful, but an old note about an allergy could be incomplete or stale, so a safety-critical fact should be confirmed. More stored text also does not guarantee perfect recall. Retrieval and context use can both fail. Here is the mechanism at an agent center. Inspect the goal and state. Choose an action. Request a tool or ask the user. Observe the result. Compare it with the success criteria. Update state, then repeat. Search, observe, update. Calculate, observe, update. Ask, observe, update. The loop ends when the outcome is verified. The user stops it. A safety rule blocks it. An error requires help, or a limit such as maximum turns is reached. A failed search is not always a failed task. No tables at the first restaurant is new evidence that helps choose the next route. The essential capability is adapting to observations rather than blindly following one fixed sequence. The flexible loop can also amplify mistakes. Suppose it reads the total budget as 4,000 per person. Later searches may look sensible while solving the wrong problem. It might select the wrong tool, produce invalid arguments, trust a stale menu, or repeat a request after a timeout. Worse, it might say a reservation succeeded even though no reservation record exists. Tool output is feedback, not automatic truth. A website, memory, or search result may be outdated, misleading, or malicious, and asking the same model to review its own answer is useful feedback, not independent proof. Reliable recovery needs a measurable check. Does this option satisfy every constraint? Did the tool return a reservation identifier? Did the actual system state change? Retries should be bounded and should change something, such as the query, the tool, or the plan. If allergy information remains ambiguous, the correct recovery is clarification or human escalation, not a confident guess. Instructions alone are not a security boundary. A restaurant page could contain irrelevant or hostile text that tries to redirect the agent. A safer design treats external content as untrusted and limits each mistake. Give it only the tools and records this task requires. Separate read access from write access. Validate structured arguments. Use normal authentication and authorization. Run risky code in a sandbox. Set limits on turns, time, and spending. Require confirmation before sending messages, spending money, or creating reservations. Keep a trace of tool requests, results, and state changes so failures can be inspected. These layers reduce risk, but no single guardrail guarantees safety. Consequential systems still need testing, monitoring, and clear human control. An agent does not need permission to do everything. Autonomy is adjustable. Our dinner agent may freely search public listings, compare menus, and calculate estimates. It should pause when information is missing, when constraints conflict, or before the booking tool changes the outside world. For a predictable task with a fixed path, deterministic code may be cheaper, faster, and easier to test. Agents are useful when steps cannot be predicted and the environment provides feedback. More agents are not automatically better either. A single agent with clear tools is often easier to understand than several agents coordinating imperfectly. Now run the fictional example. The agent stores the party size, time, area, total budget, allergy concern, and approval rule. At Illustrative Cedar table, no table for 6. At Blue Lantern, a table exists, but the illustrative estimate fails the budget. At Garden Circuit, the estimate fits, but the allergy policy is unclear, so that requirement stays unresolved. Finally, Illustrative Quiet Mango returns availability, an estimated total of 3,700 rupees, and a stated allergy contact process. The agent presents the evidence and asks the user to approve. Only after a clear yes does the application enable the reservation action. The booking tool returns an illustrative reservation identifier, and the system verifies the date, time, and party size before reporting success. The useful result was not a polished list. It was a verified outcome reached through controlled decisions. A practical agent combines a model, clear instructions, limited tools, current state, selected memory, environmental feedback, stop conditions, and guardrails. Its power is not knowing everything or narrating a long internal monologue. It comes from choosing a step, checking what happened, revising, and stopping when complete, or when a human should take over.